Hi there. This is AP Physics 1 equations that you need to know that aren't on the formula sheet, 22 to be exact. Now, some of these aren't necessarily equations, but these are just very helpful things to remember for your AP exam that you can't really just rely on your formula sheet for. Okay, so gotta move this thing. Don't memorize these. I mean, you can keep them in the back of your brain, but you need to know how to derive them. So it's not bad to memorize them, but you don't have to necessarily because most of these still can be found by deriving equations. But if you do memorize them, just make sure that if they ask you for an equation, you don't just write it. You have to derive it. So if it's saying, find the escape velocity, which is the velocity needed for something to escape an orbit, we'll look at that in a minute. But if it says that, then don't just put the equation if you memorized it. Make sure that you derive it, and I'll tell you how to derive them on here. And if you see this asterisk, that means it's very important. If it doesn't have the asterisk, then it may not even be on the exam, but if it has an asterisk, it probably will be. And these are more important for the FRQs. All right, the first one. This is a pretty important one that you may see. This is about circular motion. The centripetal force is equal to the gravitational force, both gravitational forces, whether it's the big G or small g, which is equal to ma, mass times acceleration. Now, why? Well, we'll look at this later on, but the centripetal force is a net force, so it equals ma. So you need to remember this. And the ones we'll look at in the next few that we'll look at actually are based off of this. But so here's an example of why you might want to use this. If you're trying to find acceleration due to gravity, you might want to set small g equal to big G. And if you know small g is mg, and it's always m2g, so that just means it's the smaller mass. So always remember that, smaller mass. So then if you were solving this, then the m2s would cancel out, and then little g equals g m1 divided by r squared. So that's how this might be useful, but also for these things. So, well, what is minimum velocity? This is also called critical velocity. These are the same thing. This is the minimum velocity needed for something to make it around this vertical circle. So, hopefully you can see this. If there's something that's going around this, what is the velocity needed to make it around there? If it's less than this velocity, then it will just go back down or fall off. So this equation is useful for roller coaster builders, honestly, because then you'll know what won't make the thing fall off. So, and this is a possible free response one. Think about that. Like if it's rolling at the top of a hill, they'll want you to know, okay, starting with potential, going down to kinetic, and then you know what I mean. So I'm not really teaching content on this video. I do have videos for that will be displayed at the end, but yeah, that's not what this is. But anyways, it equals the square root of g times r. That is pretty easy to remember. So if you do happen to memorize that, know how to derive it, and this is how. Just like on this one, you set fg equal to ma. Well, in this case, it would really be the small fg. But so remember, you can change a centripetal acceleration to v squared over r. So then you have mg equals m v squared over r. The m's cancel out, so then you have g equals v squared over r. Then you rearrange it, take the square root, and that's how you get it. All right, now this is what I was already saying. So this is kind of a repetition of number one, but remember that the centripetal force is a net force. So that's why it equals MAC, because the other forces are not net forces, so they don't equal that unless there's no other forces in that direction. And this points to the center. So remember, for vertical or horizontal circles, net force or centripetal force is towards the center, acceleration is towards the center, and velocity is tangent to it. And that means that if it was to stop randomly, then it would follow that tangent path because of Newton's first law. Object in motion will remain in that motion. That's inertia. All right. Now, escape velocity. This is another way how you could use number one. Escape velocity, I already mentioned this, but this is the velocity needed to escape a orbit. So let's just say that the Earth is, well, we know the Earth is orbiting around the sun. What velocity would the Earth need to have for it to just go, which that would be bad because then we would freeze. But this tells you it's the square root of g, or remember that thing, it tells you what that equals on the formula sheet. It's a constant, gravitational constant. I think 6.67 times 10 to the negative 11th. So times mass 1, this is the bigger mass, whatever it's orbiting around, divided by radius. And this is how you would derive this, because remember, you have to know how to derive it. You could memorize that if you want, but that's not going to help you for the FRQs. So you would use this equation, which is on the formula sheet. Then you would change this to, remember, we can make it MAC, and we change A to B squared over R, and you always do M or M2. That's, remember, always M2 when you're doing something like on the other side. Then this is a little bit of a weird one. Then you would cross multiply C, then you would have V squared, M2 V squared R squared equals G M2, M1 M2 R. Then the M2s would the M2s would cancel out because they're on both sides. And since you have R squared and R, they cancel out, but you're left with the 1. That's just an algebra skill. So you're left with 1R on this side. So then you have V squared R equals GM1. Then you divide by R and take the square root, and that's how you get it. This one is, this should have an asterisk by it. I don't know why I didn't do that, but this is not really an equation. When I say equation, I mean like the ones that only have letters. This is still technically an equation, but this is just a fact. So for the different kinds, remember, there's 3 kinds of kinematics. There's free fall, launched horizontally, launched at an angle. So free fall is when you just drop something and it doesn't have a, okay, that bad idea. I don't want to stab myself. So like that. You would just drop it, and it doesn't have like an initial velocity. Launched at an angle is like this. It's like you throw it kind of up, so it has an initial velocity in both things. And then launched horizontally is just like you drop something off, throw something off a cliff, I should say, like that. So in any of those cases, you always, that acceleration in the x direction is always 0. Which means that the velocity is constant in the x direction too. I should have put that on the next slide. And then the acceleration in the y direction is always g, and it is negative 10 squared, or sorry, negative 10 meters per second squared. Now, negative 10, remember, this is kind of a weird thing. It has to be negative because when you sometimes have, we'll look at that. We'll see an example in a minute, but it's negative for kinematics only. All right, now we have the velocities. And like I said, velocity in the x direction is constant for all of them. Or I guess not really free fall, but it is for the, because there is no x velocity for free fall. But for launched horizontally and launched at an angle, because acceleration is equal to 0 in the x direction is constant, velocity is constant. But initial y velocity for launched horizontally in free fall is 0 meters per second. So when you're dropping something in free fall, obviously you're not giving it an initial velocity. You are giving it an initial velocity for launched horizontally, but it's only x at first, because remember, it's like this, and x remains constant, and then y increases. And this is a very helpful thing, because remember that kinematic equations, like if you're trying to find something and you have too many unknown variables, they can connect through t. Remember that x and y, because the kinematic equations have one, you have to use one for the x and one for the y things, and you can connect them through t. And I have a video about that, but that's why this is useful, because you're like, oh, I can cancel that out, so that you eliminate an unknown variable. All right, then when for longitude and angle, there is an initial velocity for x and y, and how do you find that? Based on whatever the initial velocity is. So let's just say the initial velocity was 5. Well, that's not for x or y, that's just the complete thing. But if you needed to find a component, you do 5 times the cosine of whatever angle it was at. That's just an example. Whatever the velocity is times the cosine of the angle for x and sine for y. The time, this is the time for free fall. So how long does it take for something to hit the ground? You need to be able to derive this. This one you can't really derive. So that's just one that you would want to memorize. Also these, because they have numbers. But this one, though, you need to derive. And this is how you do it. You use this kinematic equation, and you make it in terms of y. The initial, or the final y is 0 because it hits the ground. And like I already told you, that's why it's useful to know that fact. The initial y for free fall is 0. So that's 0. So then it just is this. Initial y equals 1/2 gt squared. Technically negative, but this is what I was talking about with the negative thing. That's how it ends up being positive, because technically g is -10. That's a little bit of a weird thing, but that's just something you have to know, because you can't take the square root of a negative. So that's how you derive it. And this is the same thing as h, just so you know. It's the height. All right, now this is very important. These are the equations that you might just already memorize. These are like the first equations you learn, but this is how we relate linear displacement, velocity, and acceleration. So you might remember that velocity is change in x over time and acceleration is change in velocity over time, or that they're the slopes of those graphs. So if you had velocity versus time, the slope, or sorry, if you had displacement versus time, the slope is velocity. If you had velocity versus time, the slope is acceleration. And then you can do the area under curves, like if we rearrange these. But how do you get those? Well, it's still from the kinematic equations. For this one, you do it in terms of x. Acceleration is 0 for x. That's what it's always like. So then really we can just change this to v, and change final minus initial is change in x. And then over here we have this shorter one that I kind of like better. If you subtract this, it's just change in velocity and rearrange. That's how we do it. It may be useful to know how to derive these, but in some cases you don't usually have to derive these, but you might have to. So that's how you would if you did. But they are very good to memorize, especially like for the graph ones, like knowing what the slopes are and area on the curves. All right, now moving on, this is like a dynamics thing. The tensions, this is not something that you can derive, but the tensions of two things are always the same. So if you have two masses that are on the same rope, the tension is always the same. The tension force is. This picture is just showing you how you could find the tension force for this block up high. How could you? Well, what you would have to do is if you knew what the friction force was, then you can use the sum of the forces in x. But let's just say friction was 0. Then you would have to do this instead. Sum of the forces in the y direction for this block, and you would find out that tension equals negative ma plus mg. So that means the tension equals that also for this one. Number 11, this one you do need to memorize, and you can't derive this. And this is not a very common equation, but it is something that may be useful to know. This is So if you may not really need this one, but this is just telling you how to find the velocity for something in uniform circular motion. So 2 pi r we know is the circumference. So that kind of makes sense. Circumference times the revolutions, isn't that displacement? Yeah, it is. And then you divide that by time. So it's really the same as the kinematic one. But this is just saying this is 2 pi r times number of revolutions is the displacement and for something spinning. Okay. This is, wake up if you're not awake. This is like probably the most, well, the momentum one is important, but this is like one of the most important ones. That's why there's definitely an asterisk. Initial energy equals final energy. You will definitely use this equation on your exam. I know that for sure. Well, I would expect that because I'm pretty sure it's been on every single thing. It is a major, major topic. Not saying that I know the exam or anything, but now this is not always something that you can use if energy isn't conserved. Well, no, that's not true necessarily. That's not what I meant. I meant that the initial energy might not equal the final energy for kinetic, or I don't know what I'm trying to say. Sometimes energy can be dissipated as thermal, but you can still use this equation. So like if something was sliding down something, the initial would be potential and the final could be kinetic plus thermal. So I'm just saying this initial mechanical energy is not always equal to the final mechanical energy. So this does not mean that all mechanical energy is always conserved, because it's not. But this is what you use, and this is the law of conservation of energy. So in most cases you will use this, but that doesn't, what I mean by this parentheses thing is, don't think that means that mechanical energy is always conserved, because it's not if there is outside forces or energy dissipated, whatever the case may be. This one is, it actually kind of is on your formula sheet, but I just wanted to say it to make it clear. This is change in momentum equals impulse. So that is kind of a worthless thing because that doesn't really tell you anything. They never tell you the impulse is the change in momentum is usually. They would just tell you these things. So it's more useful to know this. Mass times change in velocity equals force times time. So that maybe you may see this and say, okay, well, the area under the curve of a force times time graph, or force versus time graph, is change momentum, or the mass versus velocity graph, the area under curve for that is impulse. You might just say that, that's what it means. Okay, this one is this is a little more straightforward than the energy one that we were just looking at. This is always, always, always true. And remember what I said about this one. This is always true, but it doesn't mean mechanical energy is conserved. But momentum is always conserved, always conserved, always conserved, always conserved. Basically, if you see a multiple choice question that says momentum is not conserved, eliminate that choice, eliminate, done. It's always conserved. Initial always equals final. That is very important. And then once we know that, we can do this. This is very important also. So this is not really something you can derive per se, but there's two kinds of collisions. Remember, elastic, that's when two things, let me see, I don't want to, okay, so let's just say okay, so two books. This is when it's like this. See, they bounce off of each other, or at least it's like this. Like they don't connect, or they don't stick together. So some of these things may be zero depending on the problem. So if it says mass 2 is at rest, then this would be 0. And so it would only be this. But this is just if they all had initial velocities and all had final velocities. Kinetic energy is conserved. Inelastic is when it's like this. They stick together. Kinetic energy is not conserved. Sorry that I didn't put those zeros down there. And really, if you notice, the only difference is that the masses are combined and they have the same velocity. That makes sense. That's very useful to know. Now, this is something that's not commonly said, but this is an important one too. But I didn't put an asterisk there because it's not that common, but you may see it, so pay attention. This is, we're using the this equation, initial energy equals final energy, but we're doing this in terms of elastic collisions. So the initial kinetic energy of a mass plus the initial kinetic energy of another mass equals the final, but it's sort of like mashing together energy and momentum. If you see, we have 1/2 mv squared, 1/2 mv squared, 1/2 mv squared. The only thing that's different is that you don't get like confused by these subscripts. That's just telling you what mass it is. So that kind of makes sense. I mean, you add all the kinetic energies and there you go. And if you wanted to know the energy lost, you would do final minus initial. Okay, this is very important. Total mechanical energy is not, it is kinetic energy at its maximum or potential energy at its maximum. It is not them added. That is very important. So if it was them added, that's not what it is. That's like, if it was them added both at their maximum, then that's 2 times what it is. So remember the graphs at its maximum, that is the total mechanical energy. That line just stays constant. So that's important. 1719, that's not good. I skipped a number. Well, just pretend that there was an 18. Okay. This is the center of mass equation. So the center of mass equation, what is that? Well, center of mass is sort of like if you have 2 different masses, it might tell you what is the something for a center of mass. And the center of mass just means like sort of the distance between them. But sometimes that center of mass can mean system. This is not a very common concept. But if you were asked to find it, you do mx, add all the mx's depending on how many masses there are and divide them by the sum of the masses. And this, you would want to memorize this because you can't really derive this. This is not an equation, but this is like something that is good to know. 1 revolution equals 2 pi radians, which equals 360 degrees. This, you may have to convert between these units, but this is also not that common, but you may have to. So just be aware of that. This equation, this is one of the kinematic equations for rotational motion. And as you can see, for some reason, they don't put that on the formula sheet, but that is for no reason because they put the other 2 on there. But this isn't that hard to remember because it's just the same as the other one, but you just switch it out for the rotational variables. All right, the last equation thing that you need to remember. This is something that's sometimes hard for people to remember, but it is very important. Okay, this is, well, this may or may not be something that you see, but if you had to convert between a linear variable and an angular variable, this is how you do it. And this is not on the equation sheet. Angular equals linear times the radius. That's what you do. So as you can see, the angular variable theta is equals xr. W, I know that's not W. I always say that, but I just hate saying omega. Equals VR, and alpha, that angular acceleration, equals AR. Do memorize this. And a way to remember this, that it may or may not work for you if you don't know what this is, but it's also on the background if you see. The show MacGyver, the main character is MacGyver, obviously, and his first name is Angus. So, and in that picture, it looks like he's eating something. And let's just say he's eating his dinner. So ang equals dinner. So that might be useful to remember. Ang equals dinner. Just remember that picture of some man that on a show that you may or may not know, but he's eating dinner. Dinner. Ang equal to dinner. All right. So there you go. Thanks for watching and good luck. These are very useful things to know, and good luck on your exam if you're taking it soon.